Hi everyone, welcome to the series of AP lectures. This is the AP Physics series, and what we're going to do, the way we're going to do this, there are two types of AP Physics exams. There's the B and the C. Some of you might be confused as in, what does that mean? What's the difference between B and C? The way I like to interpret B and C is that AP Physics C requires calculus, and AP Physics B does not. The main difference between the two, besides the calculus part, is that C is very focused and basically mimics the college physics curriculum in a sense that it has two parts. The first part will be pure mechanics, and the second part will be pure E&M, electricity and magnetism. AP Physics B, which I would call the non-calculus AP Physics, is very close, the curriculum-wise, is very close to actually your high school physics curriculum. So it covers the mechanics at E&M, but also has topics like waves, modern physics, and circular motion, and other topics that kind of been covered in your physics, regular high school physics curriculum. So the way I would look at this is that if you are comfortable, or if you think you did well with high school physics, Physics B is basically an extension of that. You're going to cover the same topics, but in a little bit more depth, and the problem will be a lot closer to what an actual college physics curriculum problems are like. So a lot of kind of long essay questions, things that involves multiple steps, and things of problems of that nature. Physics C involves calculus, so if you're taking AP Physics C, you should be actually taking calculus either at the same time, or you already have taken physics, calculus. It requires you to actually have some basic calculus handling skills, nothing big, just differentiation, integration, and a little bit vector manipulation. So it's not much of not a lot of depth required, but you do need to know how to take a derivative or how to integrate an expression. So things that we will go over. So depends on what you are comfortable with. You can either choose to take AP Physics B or choose to take AP Physics C. C in college is more geared towards math, engineering, or science-related majors. AP Physics B kind of is the college course, physics course for more humanities or kind of biological science-oriented fields. So, and once you make that choice, you can follow either the B lecture series and the C lecture series. So this is how I'm thinking I'm going to organize all the lectures. One, I'm going to actually, there are a lot of overlaps between the two topics. So the way I'm going to do this is if you look at this, you have AP Physics B/C, and the topics, BC means that this is a topic that's shared by AP Physics B and C. So I will have to go through all the common topics that are shared by both, and if you are interested in AP Physics B, I'll have additional topics that related to B, and then by the same way I'll have additional topics related to C, and then you can follow whichever curriculum that you want to follow. And for B only lectures or C only lectures, it will just topic B or topic C. So hope that clarifies a little bit. As we go through the topics, you realize the BC topics are very similar to the topics that you went through in high school. We're going to go through it in a little bit depth. We're going to actually talk about my interpretation, how to kind of deal with these problems, how to understand these concepts. My approach to physics is very simple. Minimal memorization of your formulas. There's way too many formulas. Don't need to memorize all of them because that's not practical. Because we all have a certain amount of limited memory. You don't want to waste them memorizing all physics exams. So what should you do? What's your approach to physics? The approach to physics, the right approach, is to understand it. Physics is a very simple topic. It's about whether or not how things move, why things move, right? The reason behind a motion. So we want to understand it. Once you understand it, you just need to know the basic principles and the basic fundamental equations. You can derive everything from there, and it helps you understanding it. It makes everything so simple, and in case there's a monkey wrench thrown at you in terms of deviation from the normal problems you're used to, you can still go back to the roots. If you understand it, you can derive the new way of solving the problem. So that being said, let's begin. So instead of diving right into physics, there's one topic that's really important in physics. Some of you probably already know, went through math classes, but some of you haven't. So I figure let's bring everyone back to the level field. Let's talk about, I call it topic 0 because it's not really a physics topic, it's more of a mathematical topic, but it's crucial. It's crucial to understand this, and a lot of students didn't understand this when they go into physics, and makes their life miserable because it's the language that physicists use to talk about things, to discuss things, to talk about space, to talk about time and other dimensions. But if you don't understand language, it's hard to understand why certain things are done. And I encounter a lot of questions about various understanding that can all be solved if you have a basic understanding of this concept of vectors. So let's get right into it. Topic 0, I just want to go over vectors. What are vectors? Well, vectors are defined as something that has two components. It has a magnitude plus a direction. So what's magnitude, you ask? Well, magnitude simply means a length or some kind of scale, right? And a direction is very clear, you know, which direction you're going. You say, well, that's kind of simple, right? Vector is magnitude, so length, let's use the best example. If you're walking, right, how far you're walking, how far you're walking is the magnitude, right? And direction is what? Well, I'm walking north. That is the sense direction. Now, if you think about it, everything in physics is based on this concept of vector because you know two things to be able to locate yourself, right? Because if we're talking about motion, physics is all about motion, right? You change your location. Motion is the source of everything else. Now, if you're talking about motion, you need to know two things. You need to know how far you're going and where you're going, right? Now, so in a regular sense, if you go and tell me, hey, I'm going to walk a mile. If you think about it, if you start off here and then you say, I'm going to walk a mile, do I know where you're going to be? In real life, I do. Because if I know you, I know if you're going to school, you say I'm going to walk a mile, you're going towards the direction of school. But if I'm a complete stranger, if you say I'm going to walk a mile, there's no way I know where you're going to be. Why? Because walking a mile, if you start off from here, could be what? Here. If that distance is 1 mile, right? It could be here, right? It could be there. Or you decided to do half a mile here and half a mile there, right? Or you can just walk around for 1 mile, end up where you are. There's no way for me to know where you are if you simply tell me the magnitude, right? It's a very weird concept. You think about it because we know. Because if we're telling someone where we're going and we know the person, in our head we can make up the direction part. But in physics, we always assume that no one knows what you're talking about. You have to be very specific. You have to be very scientific. So if you say you're walking a mile, I say I have no idea where you're going to be, right? All I know is you are going to be within this mile radius circle. That's it. So if you think about it, the way we describe location or movement is very inadequate in physics because it's not precise at all. Because in our head, we have our own assumptions, right? So it's important to know when you say you're walking a mile, where, in which direction you're walking a mile. Let's change this up, right? If I'm walking a mile exactly north of here, I know exactly where you're going to be because you're going to be here, right? If you say I'm walking a mile east, you're going to be here, right? Or if you say I'm walking a mile 45 degrees north of east, you're going to be here, right? So if you see, if I mix in the direction part, your description becomes precise. And physics is all about precision. Physics is about knowing where you are at what particular time, okay? So what have we been using? What have we been using when we say we just walk a mile? We only describe something called using a magnitude, and there's a name for it. It's called scale. Okay? And that means it's magnitude only. Okay? We're used to that. We're used to this scale concept, right? We always say, all right, we're going to jog for a mile. We're going to jog for 5 miles. We only have the magnitude. We don't have the direction because we assume we know where we're going. You have to change that concept. You have to understand in physics, it's all about vectors. It's no longer about scalar, okay? Scalar quantities. We are only talking about vectors. There are a couple scalar quantities that we deal with, and I'll point them out. But the first shift you have to do, or in your head you have to know, is ask yourself, okay, I don't just want to say how far I'm going. I want to be more specific. I want to say how far I'm going and where in a direction I'm going. That's crucial because if you have that built into you, it becomes very, very easy to understand a lot of physics problems. And we'll see that from this point on. Okay? So, there are two kind of quantities, right? I just explained there's the vector quantity and there's a scalar quantity. Let's focus on vector quantities. Okay? Something that has a length, or in other words, magnitude and a direction. How do I express a vector? You've probably seen this. Vector always starts with where you start and a little arrow thing, right? And then say this length is 1, so that's a 1 vector. And you can say, oh, this is vector A. It's always just a letter with arrow on top, right? Look at this. This gives you two things. It gives you what? The length of the vector. Pretend this is A, right? And this is 1, whatever unit of length is. And also gives you what? A direction, right? Which direction I'm walking. So if I say, hey, guys, I want you to walk in this direction, you can totally do that, right? You can follow my direction and walk, and I can find you exactly where you are. Okay? Let's put another vector here. Right? This is a different vector B. It's the same length. So in the scalar quantity, we can't tell the difference. But in terms of directions, we know exactly where we're going. Right? Going this way and going that way. Okay? So basically, vector is a way of describing everything in physics, and I want you guys to be very, very familiar with the concept. So the natural question is, all right, what do I do with this? How do I operate with vectors? Or the most important thing that you need to know is this concept of vector addition. How do I add vectors? Okay? Well, there are two ways. One, graphically, if you want to add vectors, it's very simple. It's just add head to tail. Okay? Add the head of the first vector to the tail of the second vector, or add the tail of the second vector to the head of the first vector, and you will get the result. Right? Okay, let's use A and B for example. A looks like this, B looks like this. If I want to add A, okay, and then B looks like this, right? I literally, what I'm going to do is move B, the tail of B, to the head of A, okay? So this is B, right? And this is your A. Okay? So if I'm adding vectors, I'm going from here to there, and I'm going to walk from here to there, that's where I'm going to end up. So the sum of the two will be a vector that looks like this. We call R. Okay? Vector R. And R stands for resultant. Really just fancy word for the sum of vectors. Okay? So A plus B equals R. Think about graphically what I just did. What I just did is I'm saying, hey, guys, I want you to follow the direction of A, right? So you walk from here to there, that's fine. And then afterwards, I want you to follow direction B. So you follow direction B, you go at this angle, you go up, right? You end up at that point. Then the sum of my commands, or what I order you guys to do, is what? This resultant. So instead of doing this and that, you can simply do what? Go from here to there, follow the trace of direction vector R, and you will end up with the same result. Right? That's what addition is, right? The sum of the two will get you the final result. The sum of these two vectors will get you the result of R. resultant r, vector r, also has its what? Also has its magnitude and also has its direction. Okay? Right? How do we get that? Well, we'll talk about this. But graphically, conceptually, this is what I'm doing. Right? This is what I'm doing. If I say, hey guys, you know what? After you're done with B, I want you to add another vector C to it. This is basically 1, but just flat to the east. Can you do that? Absolutely. What you're going to do is, again, head to tail, head of the vector, the resulting vector, and add tail to it. So C will look like this. Right? Now, what's the result of A plus B plus C? From the bottom, where you start, that's it. Okay? So graphically, it's really easy to add vectors. Just have to remember, head to tail, right? Adding the vectors, head to tail. And if you have 20 of these, keep on adding them, right? The resulting vector, or how far you've gone, is always going to be where you started from the first vector to the tipping point of the final vector. Right? That's it. Okay? Graphically, this is what you do. Right? So you say, okay, that's great. Mathematically, what do I need to do? So now that you know graphically, you simply need to do head to tail. Let's look at mathematically. Mathematically, there are a couple ways. If you think about it, what I just did, right? A and then B, and this is my resultant, right? It's not 2, right? You see, the problem is that A plus B is not 2, right? Because it's a triangle, we know that can't be, that's not 2, if they're not in the same direction. So, what do we do? Well, you said technically you can use, if I'm giving you the angle of A, and I give you the angle of B, right? You can say, all right, I can use basic geometry to figure out what this angle is, and use law of cosine, right? And use law of cosine to solve the side across from the unknown angle, right? Not really that easy to do, and no one ever does that in physics anymore, okay? The most popular, the simplest, most straightforward way to do this is what I like to call vector decomposition. Okay? Vector decomposition. What is that method? Think about it. I can't just add A and B together and say it's 2, call it a day. Why? Because they're not in the same direction. But think about this. If I have a vector, let's say vector 1 that looks like this, and I have another vector 2 that looks like this as well, what is the sum of vector 1 and 2? That you can add, it's going to be what? It's going to be 2. Why? What allows me to do just add the 2 numbers instead of that case? Because they are in the same direction. So as long as I can make vectors into the same direction, then I can just add them. Right? In other words, what I want to do, I want to standardize vectors. So these are all 2-dimensional vectors. How do I standardize them? Well, I know how to describe 2-dimensional things in standardized ways in what? In x and y coordinates. Right? So let's take vector 1 as an example. I can decompose vector 1, or vector A, into AX and AY, assuming I know the angle theta, or theta A. Why? AX is just the x component, or the component of A that's parallel to the x-axis of A. What is AX? AX in this case is what? A times cosine of theta A, right? Because this is a right triangle, that's fairly straightforward. AY is what? A times sine of theta A. That's it, right? That's pretty straightforward. You say, all right, cool. How's this helping me? Well, this alone doesn't help you, but I'm going to do the same thing with b. Okay? I'm going to take b and decompose it. B, in this case, this will be bx, which will be b times cosine of theta b, right? Assuming this is theta b, I have to give you the angle because I give you a vector, right? I have to give you length and a direction. And this is what? B of y is equal to b times sine theta b. Okay? Right? You see that? Now, what does this do? What this does is very simple. I'm going to go to this final chart, decompose A into AX and AY, right? And then for B, I'm going to decompose this into BX and BY. All right, so well, this looks still way too complicated. It's not, because what I'm going to do, I'm going to take this BX and move it down right here. I'm going to take this AY and move it out like this. Okay. Let's get rid of that. What did I just do? What is AX plus BX? AX plus BX is going to be RX, or the X component of your resultant, right? Think about it. This vector, which is straight line vector because I standardize everything into AX and BX, is going to give me RX, right? And then the same logic, AY plus BY is going to give me RY. Okay? And I can literally just add, if this is 2, this is 3, I can just literally add them. Okay? Very simple, right? Add the sum of them. And you're going to get your R. What you get is a very, very simple right triangle. To get the magnitude of R, we know that R squared is equal to Rx squared plus Ry squared. Right? Pythagorean theorem. The two legs, right, is going to give you R squared. And the angle theta of R, tangent of theta of R, is going to be Ry divided by Rx. And that's it. Okay? See how it's done? Right? So it's all about taking a vector, decompose it, right? Decompose into, I mean, these are all numbers, right? I have to give you the length, I have to give you the angle. So you can get AX, you can get AY, right? And then same thing here, B, you get what? B cosine theta, you get BX, and you get BY. So you add up the X components of the vector to get your R vector, right, in the X component. You add up the Y components of vector to give you Y component of the resultant vector. Once you get Rx and Ry, this R is simple because it's a Pythagorean triangle, right? It's a right triangle. Simply do R squared is equal to Rx squared plus Ry squared. Get the length, and if you want to get the angle, it's just R. The tangent of the angle is just opposite over adjacent, so Ry over Rx. Okay? And that's how you do this. So, let's take a look at another example, see how simple and straightforward this is. What if I have a vector that looks like this, right? And another vector that looks like that. Does it matter? No, it doesn't. What am I going to do? I'm going to take A, decompose into AX and AY. I'm going to skip the little arrow sign just to be concise, okay? And I'm going to take B do bx and by. Right? What does your r look like? This is what your r looks like. Right? So what is your rx? Rx is technically ax plus bx, right? Vector speaking. But in this case, your bx is the opposite direction, right? So you move your b down, you realize that if you connect head to tail, b looks this way, right? So this is your rx. And an ry is simple. It's just the sum of the two. Oops, wrong color. Ry is just that. Okay, so hypothetically speaking, if ax is 10, bx is 7, rx is going to be what? Because they're in the opposite direction. When you're adding them, you're what? Actually subtracting them. So this is going to be 3, and whatever this is, maybe 10, 12, whatever it is, and you still get your rx and ry, and you figure out the angle, you figure out the length, you're done. Okay? Practice how to handle vector additions. This is the fundamental concept of physics. You're going to do a lot of these. You're going to have to encounter a lot of these. You have to know them so well. Okay? But it's not that hard, right? Decompose, add the components, and you're done. Now, whatever is applicable to 2-dimensional is applicable to 3-dimensional. Okay? So practice vectors, understand vectors. Know that in physics, you're in a different realm. You're really talking about scalar quantities. You're talking about vectors all the time. So be friends with them and know how to operate with them, and you'll be fine.